Instructor Allison online tutorials. In this video I will be solving these three questions, and then I don't intend the video to be that lengthy, so I'll be fast in getting solutions to these three problems, and all of them are A-level physics under modern physics. So let's do justice to these problems. The first question says, what is the decay constant of uranium-235 that has a half-life of 15 days? So, but then under radioactivity that talks about the spontaneous emission of radiation by an element, we deduce an expression, and also for that of half-life we also have an expression. Maybe in the next video I'm going to do a full tutorials on radioactivity, so I can talk about the derivations of the expression for half-life and also for that of a radioactivity decay, radioactive decay. All right, for this we have the following parameters. We are to calculate for the decay constant, and decay constant we usually use lambda to represent the decay constant, and then for half-life we use T half, and this value is given as 15 days. It could be in year. If it is in year, already you know that 1 year gives you about 365 days. So if you want to convert from days to that of year, it should be 15 divided by 365. All those ones are simple parameters, but we're going to work with days. And then what is the decay constant? This is what you're going to look for. But there is a formula for this, and the formula is this lambda equal to 0.693 divided by T half. So lambda, which is the decay constant, will be equal to 0.693 divided by the number of days is 15. So let's use our calculator and put down what will be the solution to this. Okay, let me get the calculator as fast as possible. Okay, now we have a 0.693 divided by 15, and the result to this will be, therefore this will be 0.0462 meters, because it is decay constant and it is measured in meters. So you can see that is the solution to this first problem. Then for the second problem, what is equivalent? The equivalent of 1.00777277 AMU in MeV. So that is simple. The first thing we need to understand is the value. 1 AMU produces about 931.5 MeV. Alright, so now we are asked to calculate for this value of MeV. Convert this one. What is the equivalent of this to this? That means for us to get this value, we can say that we just use this value to multiply by this, and that will give us in this MeV. That's simple. It's as simple as that. I don't want to go by the mathematics of it by saying this one is equal to x and then I cross multiply and then get the answer. Simple too. So you could just say 1.007277 multiplied by 931.5, all will be in MeV, because we are converting to mega electron volt. That is what this stands for, mega electron volt. And this AMU means atomic mass unit. So do not forget the full meaning of this MU. We are converting from one atomic mass unit to this mega electron volt, and this is the process. So the next thing I'm going to do is to punch 1.007277 by 931.5, and this will give us the result as 938.28 approximately mega electron volt. So that is the solution to that second problem. So the last problem is for us to evaluate the de Broglie wavelength of electrons waves passing through a potential difference of 200 volts. So the simple way we can address this problem is that we're going to make a lot of derivations or assumptions before we can be able to arrive at this. And one of the way I want us to go about it is to think about the acceleration of this electron. The electron accelerated by passing through a potential difference of this. If you can check by de Broglie wavelength, we have this Planck's constant all over mass times velocity. But in this question, you can see that we don't have this man. This is volt, not really volt velocity. This is volt, 200 volts for potential difference of voltage. And the electron, wavelength of electrons, that means we need to make some sort of calculations. And if I'm going through the details, it will take more of that. I intend to make this video not more than 3 minutes. So in that regard, we can say that electron volts will be equal to kinetic energy. And this is the expression for kinetic energy because it has to accelerate accelerations. When a body is accelerating, it is a motion, and then the kinetic energy there will be observed. So the electron volt will be equal to half mv squared. And at this point, we can make the velocity the subject of the relation. And if we do that, you can see that v squared will be equal to, if this cross multiply, we have a 2 electron volt all over the mass. All right. Then finally, we can make this v the subject of the relation by saying v equal to the general square root of 2 electron volts all over the mass. And what is this mass? This mass is the mass of electron. And the mass of electron has its value as 9.11 times 10 to the power of that. So what we need to do, this is electron, and the electron has its own value also. So we're going to just substitute all these things into the, to get this v, then we substitute into the expression. So now v will be equal to the general square root of 2 multiply. Let's use our calculator to get some of these things fixed. The value for electron is 1.6 times 10 to the power of minus 19, and this will multiply by, this volt is 200. All right, all divide by the mass of electron is 9.11 times 10 to the power of minus 31 kilogram. All right, so let's have this value fixed. Let's point this. The first one we have is 2 multiplied by 1.6 times 10 to the power of we have minus 19, and this will multiply by 200. Okay, and the value we have here on the numerator is 6.4 times 10 to the power of minus 17. This divided by 9.11 times 10 to the power of minus 31. And then if you divide the result you have by 9.11 to the power of times 10 to the power of minus 31. All right, the result you have here is going to be 7.025, all right, times 10 to the power of 13. So finally, we're going to check for the square root. We're going to check for the square root of the answer. We're going to check for the square root of 7.025 times, we're having it twice. Okay, 7.025 times 10 to the power of 13. And this will give us the result of, therefore our velocity will be equal to 8381527.307 meter per second. All right. Now we've gotten the velocity, we need to calculate for the de Broglie's wavelength. And in order to do that, we have to adopt this formula. And the formula is lambda equal to Planck's constant divided by mass times the velocity. We've gotten the mass, we know the mass already, and we also know the velocity, which is this. The mass is the mass of electron, all right? And also this is Planck's constant. So let's create a space for this. Let's leave a space here so that we can be able to substitute the value into it. So our de Broglie wavelength will be equal to, Planck's constant is given as 6.63 times 10 to the power of minus 34. All right, and this will divide by the mass of electron, which is 9.11 times 10 to the power of minus 31. This will multiply by the velocity, which is 8384. Okay, 8381527.3. all right, approximately. So by the time you put all these values together, you will see that the de Broglie's wavelength will be 6.63 times 10 to the power of 10 to the power of minus 34. This would divide by the product of this 9.11 by 10 to the power of minus 31, and this multiplies by 1527.3, and this will give us the result of 8.68 meters. All right, this is for de Broglie's wavelength, and the wavelength is measured in meters, and this will be the solution to this problem. If you find any difficulty in understanding the concept, please drop the comments, drop the issues you will be having, or maybe the challenge you have in the comment section. Then I'm going to address it in no distant time. And if you've not subscribed to this channel or my channel, please do so, and like the video, share, and also make sure you follow us up on our next exercises on quantum mechanics. Thank you very much, and stay subscribed.